anything we find about Makran is going to be new. Some work has been done, but a lot of the data remains uh, 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 in the coffers of the oil industry in some cases, and with some academic data remains unpublished. So this is the first time you will see some new data on Makran, and it's based on a PhD thesis that was just finished only last Tuesday. It was defended successfully in Sorbonne by a PhD student. His name is Dia Ninkabu, and he originates from Palestine, but he is of it's a Frenchman, of course. He's lived all his life in France, so he is a very smart and excellent researcher, and he has shed new light on the Makran area. So Makran, of course, those of you who are familiar with it, has been is divided in two parts. We have half of it on Pakistani side, and Iran has the other half of Makran on their side. So there's Western and Eastern Makran, and they have never been studied together. So this is the first time that any researcher has actually tried to bring together these two parts and study it as a unit. And it turns out that not only East and West Makran are linked together, have a combined history, but also the northern coast margin of Oman is also linked to this area because much of the tectonics that happened in the Mesozoic and Paleogene in the Oman have also affected the subduction zone on Makran. So this particular thesis of Dia Ninkabu was actually combined these two areas of East and West Makran as well as the northern margin of Oman. So now I'm going to try and project my slides. I'm not sure whether you're seeing it. Are you seeing it? Is that okay?
Not, sir, not yet.
Okay. I'm also very happy to see that you are all wearing masks. Here in Washington, we have 70% of the people have been vaccinated, but I still go out with masks because it's better to be safe than sorry. Anyway.
Yes, sir. Also, the vaccine has been started here in Pakistan.
Excellent, excellent. Okay. Uh, so do I press a button here?
No, sir. Please check the button on the left top. It's share content.
Share, open share. Okay, there we go. Can you see it now?
Yes. Now we can see. Please, sir. You shared the screen or the window?
The window.
Okay.
It's fine.
Okay. It's okay now.
All right. So I, as I said, this is based on a PhD thesis. Mostly the research from Sorbonne University by a PhD student who was working with me and several other professors at Sorbonne. And so, of course, it covers, as I said, both the Irani side and Pakistani sides of Makran, and it also covers northern Oman margins. So there are a couple of papers that have already been either published or submitted. Journal of Geophysical Research. There was a paper published just recently, earlier this year. It's the first one. It's on Oman. Actually, you can see that the abducted margin of Oman, and this was published first because Dia finished his study of the Oman earlier than he did the Makran. And so that was published. And then there is another paper that is now in press, also mostly on Oman and on the Arabian Sea sediments. It's more on the sedimentary side. And then here is his PhD thesis, which was actually defended just this week on Tuesday very successfully in Sorbonne. So nobody has, and of course there are many more papers in preparation on Makran. So nobody has seen this data outside Sorbonne. So you are very privileged to be seeing it for the first time. Now, we call Makran a subduction zone. So I'm sure most of you are geologists, so you know what a subduction zone is. So I thought, just in case, uh, uh, to familiarize you with what a subduction zone is, I just put up this cartoon which shows a subduction zone. Subduction is a geological process in which denser oceanic lithosphere dives below lighter continental lithosphere at plate convergences. So you can have a oceanic continental convergence, or you can have oceanic convergence as well, where you can have an oceanic plate going underneath another oceanic plate. And you can decipher the shape of the zone, this lithosphere going down, oceanic lithosphere going down underneath the continental lithosphere, and you can decipher that by earthquakes. All the major earthquakes take place along this subducting slab boundaries, and this is called the Benioff zone. Or Benioff zone is where all the major earthquakes occur in a subduction zone. This produces, of course, a subduction zone. So that's a subduction zone, the whole thing. And then it also produces a trench. This is called a trench. This is the whole thing is called a trench, and then it produces a accretionary prism around behind it. So this is the accretionary prism. This is where the lithosphere is accreting. It's getting coming together in large amounts, and that's why it's called an accreting prism or accretionary prism. Uh, the subduction zones are also characterized by major earthquakes, and all, but not only major earthquakes, but also microseismicity, small earthquakes that are happening all the time. They are so small that you cannot feel them, but they are there. For example, if you put a very sensitive seismometer on Karachi, it will probably be constantly humming with microseismicity because the earthquakes are happening constantly. These are micro earthquakes. They of course, but they are also very important when we study the shape of these subduction zones and the Benioff zone. Fluids are released from the subducting plate, and it triggers volcanism. And of course, you can get volcanoes overriding and on the overriding plate. So this is the overriding plate. This is the undergoing plate, and there you see volcanoes. And this is called a volcanic arc or a back arc. Sometimes this is called the fore arc, and this is called the back arc. So these are the terms that are very often used by geophysicists and geologists who are studying the tectonics of these things. The angle of the slab is an important characteristic. If it is shallow, it produces deformation belt with crustal thickening. So there is a very thick crust if it is shallow. But if it is steep, it produces a typical back arc basin here. So Makran is an excellent laboratory to study subduction zone with relatively shallow Benioff zone and major earthquakes generated between 10 and 160 meter depth. So that depth of 10 to 160 kilometers below the surface is a very important zone. It's called the seismogenic zone because that's where most of the major earthquakes occur. Okay, now here is actually a real image from a seismogenic zone or a subduction zone. This is from the Nankai Trough. Some of you may know where Nankai Trough is. Nankai Trough is just along Japan, the east of Japan. That's where the oceanic plate, this one, is undergoing Japan. So that's Japan up here, land is here. This is the Japanese shelf, and this is the accretionary prism, and this is the plate going down. So you can actually see this beautiful seismic, 3D seismics, that these things the plate is actually subducting down, and this is the locked seismogenic zone where major earthquakes occur. And the Nankai Trophic, of course, Nankai Trough is a major example of this subduction zone. But Makran, of course, is also another type of subduction zone, but it's also a very, very important one in the world of subduction zones. This experiment obtained these very high resolution 3D seismics, 3D seismic images, which was funded by USNSF. I used to work at National Science Foundation as a director of marine geosciences, and I was responsible actually for funding a lot of this research in the Nankai Trough when I was there. So I'm quite familiar with this thing. And everything we know, now it was also drilled later on by deep sea drilling program. And as you can see, we had a very deep drill that went right through the place where the two plates meet, right through the accretionary prism into the underlying plate. And there was also some shallower holes were also drilled along the overriding as well as the underplating plate. Now, everything we know about the tectonic facies, the lithofacies that are typical of subduction zones comes from this particular experiment. Okay, I think I can. Sorry. All right. So you can clearly see the subductor and overriding plates here. All right. Now let's set up the setting of Makran in the global picture of what was going on with the plates that make up the Makran part of Pakistan. Of course, Pakistan is partly on the Indian plate and partly on the Arabian or Eurasian plate. So if you go from Triassic, this is from the late Triassic picture, and it is the present day picture, and here's the late Cretaceous picture. If you go from Triassic, the Indian plate was still attached to Indian plate is right here. It was still attached to Gondwana land, and the Neo-Tethys was a big ocean between these bits and pieces of Cimmeria and Eurasia, and then there were two oceans, one called Neo-Tethys, the other called Paleo-Tethys. Together, they later on become Tethys. So in the Paleogene, as you can see, that India has now separated, split from Africa, and but Madagascar is still attached to it, but it is moving eastwards, and it's moving actually moved very rapidly. By the late Cretaceous, Gondwana had split, and the rapid movement of India started northwest, which collided with Asia at about 50 million years ago in Eocene. And Tethys Ocean was largely closed by the end of the Paleogene, and the present day conditions actually started somewhere in the Miocene or late Oligocene or Miocene at that time. Notice the reconstructed spreading ridges. Of course, we reconstruct these spreading ridges based on models, but there is no direct evidence that these were the shapes of these spreading ridges. So these are just conjecture, but it's probably true because you need spreading ridges to be able to split the two plates apart and have them collide with each other later on. Okay, so here is now Makran in this is this study area in this triangle includes northern Oman and Makran, and also land-based sections in Iran and Pakistan. And and it is actually a continuous fold belt which goes from the alpine regions of Europe to into Asia, and then of course north right here in north of Arabia, and then Iran, and Zagros Mountains up here, and then Indian plate starts here, and the Chaman Fault is the boundary between these two plates. So you can see that it is a complicated area. Uh, so the upper picture shows you the various plates that are now in conjunction with each other, and the lower figure shows you the tectonic provinces. And here we will be talking about mostly this province, the Makran Accretionary Prism. Okay, now here again you see setting of the Makran Subduction Zone and Northern Oman margin. Um, I'll be showing you two sections here, and I'll be actually showing you some results from them. I thought it would be a good idea for you to keep an eye on some of these findings early enough so that when you look at the evidence, then you can see that the evidence is based on these particular seismic sections as well as on these models. So section A and B will be the next two slides. This is the section A, which is northern Oman margin through accretionary prism and this subduction zone right here. So northern Oman margin is here, Oman abyssal plain is here, and then here is the Makran accretionary prism, and this is the land part of that. This is the wedge arc behind it. And you can see, this is based on this summary slide is based on actual seismic data, and you can see that there is a lot of tectonic activity here in the Makran itself. There is also some obduction here of old oceanic crust in the Samail ophiolites, as they are called in Oman, which are actually have some connection with the older history of the Makran. So here are some of the findings. Key findings of this area is that infill of the abyssal plain is flat lying turbidites, mostly turbidites. Turbidites, as you know, are deposits that are formed by slumps and slides, as well as currents. And they are actually two kinds of these things. They are the ones that are sorted, well sorted, and then, of course, there are also contourites, which are collected together by currents. So these turbidites were deposited in the early to middle Miocene, and then clastic input from northern Oman during the late Miocene. So there was a lot of sediment coming down from here because this is the high relief area. And development of hybrid turbidite contourite system occurs in the Pleistocene associated with the flexure linked to Makran. So the flexure of Makran itself is causing it, and the high areas in Makran are causing sediment to come from also from the north, not just from the south at this time. And Pleistocene is deformation of the imbricate fan of Makran accretionary prism. So there's a lot of deformation that happened in the Pleistocene. It started already in the Miocene, but it became more important in the Pleistocene. Now we'll see the second slide, the second section, which goes through the Indus fan area, the distal Indus fan, plus the Dalrymple trough. This is the trough. It's a shallow, and then there is a Murray Ridge, which is a high relief, and then of course the Makran accretionary prism. If you remember, it goes right through those areas. And the findings here are active channel levee system throughout the Miocene in this area, late Miocene deformation since 10 million years of the Dalrymple trough, infilled by clastics from the northern Oman margin and development of contourites, and then intense plioplastine deformation of Dalrymple trough. This is all plioplastocene, indicated by mass transport complex. So there are these mass transport complexes here and major unconformities, complexes which are overlapping the younger sediments. Okay, now if you look at the Neogene chronology of the Arabia and its surroundings, Makran and India, the Indian plate, you can see that Makran, we don't need to go into detail of this, but just wanted to show you that when you compare these neighborhoods, you see that the Makran is quite distinct from both eastern and western regions in its tectonic history. So it's a unit by itself. It's sitting there. But it has had a very complex history, which you will see in a minute as we talk about this thing. Here are some of the old plate boundaries and the tectonic blocks that play a major role in the Makran Subduction Zone. And as you can see here, these red areas, these are all tectonically deformed areas. These areas are also highly tectonically deformed. And it's the Makran subduction. It lies. The subduction zone lies in the transition between two collisional origins. For example, here is the right here is the Zagros Mountains, and which is collisional area, and then here is the Kirthar Suleiman range, which is of course another collisional area. So between this collisional origin, Makran is right there, sitting in there, and it is affected by these two origins in its history, and the characteristics of this zone, subduction zone, are very much linked to these tectonic neighborhoods. Now, this shows an integrated structure of both Pakistani and Irani sides of Makran, the western and eastern side of Makran, and some of the major faults that are long-lasting, major faults that run right through the whole system, and also the major tectonic trends. And you can see this is the Indian plate here, and this is the Eurasian plate. The prism as a backstop is a continental block. So this continental block has imbricated ophiolites and continental material in the west. So ophiolites are, of course, old oceanic crust that has abducted now and come up and is visible in outcrops. So this is called abduction, when oceanic crust comes up by tectonic processes. That is an ophiolite. So you can see the ophiolites in Irani side of Makran, as well as in the Bella ophiolite here in the Kirthar Suleiman range is also typical of this area. These features are absent in the east. These are the imbricated ophiolites are absent in the east. But the backstop here is a volcanic arc, the Chagai Rashgo area, and the Paleogene Sistan Suture. Sistan is up here. Suture zone separates both these areas. So that's the Sistan Suture and separating the Pakistani side of Makran from, and they are not similar. They are quite dissimilar, in fact, in characteristics. These are some of the physiographic differences from west to east. The western Makran has more chaotic structures. As you can see here, there were lots of chaotic structures and few thrusts, whereas eastern, its shelf and slope transition is gentle. Shelf slope transition is gentle, whereas on the eastern side, Makran has well-defined structure. These are extremely well-defined structure, and an elongated thrust compared with the west. An eastern shelf and slope break is more abrupt. The shelf slope break, which is in here, here, is rather abrupt. It is more gentle here than here. And Zagros influence is called characteristic in the west and Indian plate collision in the east. So these two things you must keep in mind, that these two influences are really important in this area. Okay, now these are some models based on tomography mostly, which I will show in a little while. This is the tectonic evolution of Oman Makran complex, as it's now called, late Cretaceous through Paleogene. And as you can see up here, you have 95 to 90 million years in the late Cretaceous, and then from 90 to 60 million years in the late Cretaceous and late through Paleocene, and then 50 million years to 25 million years, which is Eocene and Oligocene. So you can see that there are multiple subducting plates in the late Cretaceous, not just one, but two. Maybe there was a third one at a tangent to these things. So there are multiple slabs, as they are called. So these slabs are persistent. The evolution of subduction zone in the area with multiple slabs, the late Cretaceous, and Berg was the guy who looked at the tomography data from this area, which is very, very recent, only 2 or 3 years ago, and came up with this model. And convergence and abduction along Oman up to Paleogene. So this area was abducted in Oman with possible stalled subduction. There's some stalled subduction here, probably in the forward slab. And then in the Eocene onward, there is a development of the current Makran system, which is you see here now. So these are models that are, of course, based. The evidence is from seismic tomography, and this will be the second part of my talk today when I show you that. The model shows that Makran subduction zone is also unique in that the subducting plate is linked to the old Oman margin. That's how it's linked to the Oman. And abduction in Oman actually is resulted from the fact that there was a stalled subduction, and when you stall the subduction, you bring out the oceanic crust to the surface on the other side. So that's simple physics there. Now, seismicity or earthquakes are very, very important indicators or evidence in this area. And here are on the Makran itself, more than magnitude 4 earthquakes, which means that medium to large earthquakes only. They are all plotted here. And geodesy, which is the angle at which the plate is moving. So this is the Gsp velocity vectors. These are you put down seismometers or GPS geodetic instruments that measure the movement of the soil or of the surface of the earth, wherever you put these on, and then you measure them very accurately with GPS, and you can measure them with the accuracy of a few millimeters, and they can show you how the plates are moving today. So these are the movements of the plates right now. The all of Pakistan and Makran and Iranian Makran are moving northeast direction, and these, and of course the movement is very, very slow, so you can't actually measure it except with these geodetic instruments. So there are these two cross sections that I'm going to show you, one here and one here, and the upper one is the west one, the western side, and the lower one is central Makran, western Makran and central Makran, and the central one is more towards the east, of course. The upper section is through the western Makran subduction zone, while the lower one is from central Makran. The lower section extends deep into the Helmand block in the north. So this is although central Makran, it is still mostly in Iran, and the Helmand block is up here, and it goes all the way. But the study area, the investigated area, is just extends from here to here only. So this area has not been, Helmand block is up here, but we haven't studied that. This is the part that we have studied. Okay, so now I wanted to show you also some Benioff zones. The Benioff zone, sometimes also called the Vedati-Benioff zone, depth along 3 cross sections from west to east. Remember in the second slide, I showed you a cartoon of subduction zone, and there you saw a very nice Benioff zones and all the earthquakes. Here is the Benioff zone from west to east. This is west, and this is east, and this is in the center. And as you can see, the shape of the Benioff zone are different. It is quite shallow, but it's also shallow here, but it gets a bit steep later on. There is an older part of the stalled subduction, which makes it a little more steeper. But it's also a more recent part of this Benioff zone is also fairly shallow. The subducting angle is shallow in the west and getting a little more steep in the east. Major earthquakes are between 10 and 160 kilometers depth, and that's what marks the Benioff zone, of course. And now here is are the models of active deformation in the Makran area, and as you can see, this is the red color shows the deformation, high deformation quotient, the second invariant, as they called. Second invariant in geodetic models is a measure of strain, and thus active strain-related deformation, which is happening here in the Zagros, in the Kirthar-Suleiman range, and along Makran, as you can see here. Now, this is vorticity. Vorticity is a whirling, or it is not a simple rotation, but it's more complicated than rotation, but it's also a measure of deformation. And as you can see, there is a lot of the deformation in here in this area, as well as in this area. So the Makran is sandwiched between these two deforming provinces. The Makran as expected, shows strong deformation both along the trench and two ranges, the Zagros and Kirthar, that are bound to it on the east, west, and east. And then, okay, now let's look at some of the stratigraphic differences in the Iranian Makrani side. As you can see, they are different because the backdrop of these two parts of the Makran subduction zone are different. The Irani side is different than the Pakistani side, and stratigraphy is also quite different. The Western Irani Makran stratigraphy is comprised largely of volcanic clastics, gypsiferous marls, and carbonates, whereas the Eastern Makran comprises largely of contourites, channel levee complexes, more sediments that are derived from and brought down by rivers. And major change in lithology occurs around 11 million years, when there is also major unconformities at that time too. That's where the nature of the lithology changes, and that has to do with tectonics in this area. Okay. Now, here are two sections that Dia has put together, one from the Irani part of Makran and one from Pakistani part of Makran. And these are amphibious cross-section, meaning that they go from ocean to land and ocean to land, and that's why they're called amphibious. The upper section is from Western Makran, and the lower one from the Pakistani side, eastern side. Seismic data from the study came from old legacy data obtained by many different companies in Pakistani side. I have to say a few words about the data. Now, the data is available for this study has come from many different companies, and from whom we have permissions to study this, but not to publish some of the lines that they have given us. So when I show you some of the interpretation, I will have to cover the seismic lines up a little bit, because our paperwork is still not complete to publish those things, so we cannot show them. But I can show you all the interpretations. That's okay. But even that you are seeing for the first time. Nobody else has seen them. So seismic data. Now, on the Irani side, the data was largely gathered by NIOC, National Iranian Oil Company. They contracted it out to many different companies, and this is a good 3D and 2D data. Most of the data in Pakistani side is 2D data, although more recently we have, I hear that we have 3D data as well, but that was not available to us. So it is all based on the legacy data from the companies that they were kind enough to provide us. B is the westward large scale. You can see on it's a large scale on this part of the wedge here is a large sketch of created thrust sheets. Thrust sheets are landward and imbricate faults. These imbricate faults on the basinward side, and in the eastern on the eastern Makran, you have closely spaced, deep-rooted thrust sheets, as you can see here, and so there are these differences from one side to the other as well. Now, now there is a third section which goes from here to Kirthar range, from Indus side, sorry, from Makran side to Indus side, and through Makran range, and which we will also see in the third section here. Here, you can see the subducting plate to the west is transitioning to the Indian continental crust, and you can see Kirthar, which is the part of the Indian plate, and it's all deformed and highly faulted, and then crust and the east of the Oman null fault, which is somewhere in here. And you can also see the Bella ophiolite right here. This is sitting right on top of the Paleogene. Is the abducted Bella ophiolite sitting on top of the Mesozoic strata. So it is actually right here, the black shown here is the Bella ophiolite. So this is also an important ophiolite example, and the one in one in Oman is very well exposed and very well developed. So that's why when you want to see a good ophiolite, you go to Oman. You don't go to Bella, because most of this is covered and it's not well exposed. Although it is also for petrologists, is also heaven sent area, the Bella ophiolite. Now here I'm going to start showing you some cross sections of seismic lines on which the interpretation are actually based. And as you can see, I've covered up the seismic line because we are not allowed to show them as yet. As I said, we will have permission soon, and then we'll publish all of these things. But right now, the paperwork is not complete. But we are allowed to show you the interpretation, which is the important thing actually. That's what you are here for, not for the seismic line. Okay, this is seismic data interpretations. Offshore data shows a gentle slope here and a wider shelf in the west and steeper slope in the east. Okay, so this is the difference that you should keep in mind. Wedge top mini basins, there are all these mini basins on top of the wedge right here. You see, this is the wedge, and I can see all these mini basins in here, separated from the imbricate thrusts. So the imbricate thrusts are right here, and they are the mini basins on top of these things. So individual basins. Plioplastron sediments prograde over the imbricate thrusts. So all of these that you could see here sediments that you see in yellow at the very top are the plioplastron, but they bury the faults in the east. Okay. Shale diapiers and listric faults are also seen in the west, and mud diapiers in the east. So these are some physiographic features that everybody knows about. All right. Now, paleogeographic reconstruction, and then you have seen these models, the section models before, these ones here. But here is the paleogeographic reconstruction of the subduction complex. Aptian meaning middle of Cretaceous, and Danian meaning early Paleocene. And as you can see, India in the Aptian is in the mid Cretaceous is still way down here. It started moving very rapidly after that, before it collided with Eurasia. And here is in the Danian. You can see it has moved very rapidly, and it's already here in the Paleogene. And so these are the Berg's models, which we have seen before, going from the mid-Cretaceous shows a spreading ridge, as well as the subduction accompanying magmatism between Arabia and Eurasian plates. India is still attached to Madagascar. The early Paleocene reconstruction shows convergence in neotethys and subduction between Arabia and Eurasia. India is now rapidly moving northwards, and the cross section shows single seismic zone in the early Cretaceous with magmatism changing to double seismic zones in seismic zones, sorry, not seismic, subduction zone in the late Cretaceous and Paleocene. So, and I will show you tomographic images where you will be able to actually see these old parts of these plates, these bits of these old plates that are now subducted. You will see them in the deeper lithosphere. Here, now cross section below here shows subduction zone persists until the double the subduction zone persists until the early Eocene, changing to a single one here. Sorry, already here in the late Eocene, and by early Miocene, it looks very much like the present day. Now, here is a reconstruction of the provenance of sediments. Where was it coming from? So, when you compare the sediments that have been recovered from the ocean, you look at the provenance, you see that they were derived from all of this area, and because of the uplift of the Zagros Mountains right here. There are two cross sections from the east and the west that are trying. Now here is a and B, as you can see, and these are the east is at the top now, and the west is at the bottom. And you can see here, Dia has attempted to correlate the land to basin parts of the east and west. Makran is younging, of course, oceanward. This way, ocean is this way, so it's younging this way, and becoming older and older this way. So Eocene to Pliocene, Pleistocene sediments have been mapped and represent a synthesis of previous works as well as our new interpretation based on seismic data. Here is another seismic interpretation across eastern Makran now, and as you can see, I had to cover up the seismic lines, but you can see the interpretations here very nicely. A and B are seismic lines across Makran Accretionary Prism. A map means Makran Accretionary Prism, abyssal plain, Little Murray Ridge, and the abyssal plain itself. Notice that the imbricate thrusts comprise Little Murray Ridge. So Little Murray Ridge is right here. This is the Little Murray Ridge. So it is a little higher than the rest of it, but it also comprises of this imbricate thrusts. And C and D, you can see the line and the interpretation that goes through Dalrymple Trough. This is the more shallow compared to this raised area, which is the Indus margin, and then the Murray Ridge here. So this is just to show you the structure of the surrounding. Notice the mass transport deposit along steep margins of the fault. So these steep margins have these mass transport deposits. These are chaotic complex of sediments that are derived from uptip because of steep margins. And here is the easternmost Makran seismic sections and interpretations. You can see that this is the seismic section itself, and then synkinematic strata, so that actually tell us which strata were were being laid down while deformation was taking place. That's why they're called synkinematic. And the stratigraphic ages of those, and you can see that late Miocene is predominant in here, but there is also some early Miocene and some Oligocene, and below that some Eocene as well. So there is very little well data in this area. So a lot of these age models are based on cross correlations from distant areas. So this is one of the main disadvantage of studying this area, is because although there is good seismic data, there is not enough well data to actually be absolutely certain about the ages of these. So these are probably pretty close, but they are not. You can't be absolutely certain that these ages are uh, absolutely what it says here in this legend. So you have to take that with a pinch of salt. So age module is available on a paleo data in wells and cross correlations. Okay, and now here we have another line from Central Makran, the seismic line. In this case, I can show that because you can't see much of the seismics anymore. It's just the interpreted part, and you can see again seismic interpretation, syn kinematic strata interpretation, and seismic, which also shows the seismic phases, and as well as the stratigraphic age data here. So typical imbricate part of the margin. This time from the central part of Makran, accretionary closely spaced imbricate thrusts and syntectonic strata deposited during deformation, and age model again based on little data that we have on there. And then here is the seismic interpretation for the westernmost part of Makran, and then on the Iranian side. And as you can see, the synkinematic strata again shows a lot of deformation of the sediment as they are being deposited. Here are the mini basins on top of these wedges, and the thrust faults. And here are the ages of those Miocene and early Miocene and late Miocene and Oligo-Eocene in the bottom. Okay, so I'll quickly go through that. Now, where is the sediment coming from? Sediment input pathways, and this is very important. If we are going to go for the oil in this area, then we have to know where the sediment is coming from, what is the nature of the sediment, whether any of it was organic rich, and all of those things. And for that, you need to know the provenance of these sediments. And here is a very good synthesis of the provenance. This is all new data. It has never been seen before. Inferred from the seismic data, this shows the sediment flows pathway onshore to offshore. Thick Pliocene pile of sediment here in the Zagros Mountains, because the Zagros are still, they were rising rapidly in the Pleistocene, and that means that the relief was being enhanced constantly, and that produces this thick pile of offshore sediments in this area. High Oman input along Oman margin. So Oman has also, in the abyssal plain especially, a lot of sediments come from this side as well as from that side, and they're mixing together. Okay, sediment dispersal pathways. Dia has made some models here at different times. Here is the early Miocene, is the late Miocene, and here is the Pleistocene. And as you can see, in early Miocene, major dispersal is via the Katawaz Delta. Katawaz Delta is up here. Indus Delta is down here. But this is Katawaz. This is the old Delta, pre-Indus Delta. And a lot of the sediment was coming through here at that time into the Makran, Accretionary Prism, and abyssal plain. It's a proto-delta, and it was a minor delta, but it's important in the early Miocene. By late Miocene, Indus dispersal system becomes more important. So Katawaz is no longer as important, but Indus becomes more important. And on Makran, north to south, dispersal is now established. So this is also north to south dispersal is also now possible, although it's not a major source of sediment. It is certainly because of the continuous uplift of this margin. With every major earthquake, you are making relief, and that relief provides a lot of the sediment in the trench. In Pleistocene, these dispersal patterns continue. Okay, now here is a very nice bathymetry, picture of the bathymetry. The German researchers have taken these these very nice bathymetric pictures of with their system on their ship, and you can see a lot of deep canyons are seen here on the Pakistani Makran side, but not so deep and not so prominent on the Irani side. And that's also a very distinct difference. And here, yeah, so high resolution bathymetry shows several deep canyons and tributaries in the east, and less pronounced canyons in the west. Lower figure shows a model of the size of present day sediment catchment areas along coastal Makran. As you can see, the catchment area on the east becomes and the west, the catchment areas are about 4,000, little more than 4,000 square kilometers, and here in the west, in the east, it becomes more, they become much bigger, 31,000 square kilometers in the east, and this is related, of course, to the wedge size area size. Sorry. This is also the case in Pleistocene. Fluvial input in the first order control on sediment piles along the Makran accretionary wedge. So river sediments are very, very important in this area. They have been brought in to this area. And now, summary of conclusion. Before we go to tomography, I want you to just look quickly at this the summary of that we have so far. The Makran Accretionary Prism displays two distinct morphotectonic regime, an imbricate, fan, and wedge top basins towards the coast. Deformation of the wedge top basins depends on sediment rate across the wedge, which in turn is dependent on the size of catchment areas uptip. Westernmost Makran shows thick Pleistocene accumulation source from the Zagros range and their continuous uplift, and mud content increases east to west, culminating in thick mobile shales in the westernmost Makran, where progradation of Makran wedge competes with the northern Oman gravity spreading system deformation, resulting in local mini basins in that area. Okay. Now let's look at tomography area in this second part of the talk. Here is the Alpine Himalayan range again, and here is the two pictures of tomography. One at shallower depth of 400 meters, and the other one at 1,000 kilometers. Sorry, not meter, kilometers. 400 kilometer depth, and here is 1,000 kilometer depth. And the hot areas are red, and the cold areas are blue. And of course, the subducting slabs are going to be cold. They are cold oceanic crust, and therefore they will be blue. And now, what is seismic tomography? Just a small introduction. In seismic tomography, P and S and surface waves produced by explosions, uh, artificial explosions by dynamite or earthquakes. Even earthquakes can help us produce good tomographic images. They are used to construct 3D models of velocity anomalies of the moving waves that can be interpreted as structural, thermal, or compositional variations. Okay, so tomography is, these are especially useful to study deeper core, mantle, and plate tectonic processes. This figure shows the tomographic velocity or thermal anomaly at 1,400 kilometers in the Alpine Himalayan areas. And as you can see in the Makran area here, you see some of these blue areas. That's the subducting plate, prominent in the at 400 kilometers, but not so prominent at the 1,000 kilometers depth. So, but I'll show you some more. The colder blue subducting slabs mark the location of Makran subduction zone, clearly seen in 400 meter depth, but subdued in the 1,000 kilometers. Okay, now here are some cross section. They run from north to south, and as you can see here, they are uh, fr- uh, they are actually mostly from west. They're all from Western Makran, and they run into northern Iran. So this is the Makran area, and that's run into northern Iran. So you can see that in here in this picture, but much better. And as you can see, these blue slabs represent old, colder slabs, or these are what we call graveyards of old slabs, subducting slabs. Here is the present day slab, and then you can see that there is an older bit of this slab underneath the warmer crust above. And you can also see further deep older parts of the slab as well. So again, you can see in these models, especially in H, right here, this has been modeled, and there is consistent. The red means that all the models show consistent velocity anomaly in this area and this depth and this depth. And the red doesn't mean hot here; it means that higher number of certainty, higher number of certainties, that slab was here and slab was here at some time in the past. So all of you can see the cold Makran slab subducting underneath the warmer Iranian lithosphere. H shows the warmer colors with the slabs where images of the slab agree most, and I shows the cross section that was the image. Okay. Here we have now a strike cross section. You can see that it runs east-west here. The other one was north-south. And as you can see that here also, you can see bits of the old Indian slabs that were actually produced by the moving Indian plate when it was subducting underneath the Indian, the Eurasian crust. And here is the bits of the Indian. Here is Arabia, here is India, and then of course there are the Zagros also has its own slab, and the Afghanistan has its own slab underneath. So these are all slabs that are buried underneath these continental lithospheres, which were active at another time. That's how we know that there were old subduction zones here, fossil subduction zones that are no longer visible to us because they're all being subducted down below the continental lithosphere. Okay. This is why geoscientists have constructed history of subduction in the Oman Makran region as that of multiple subduction zones, as evidenced by multiple slabs. Now these are a couple of dip sections, more pertinent to Makran itself, and as you can see that they are from different central Makran, eastern Makran, and then western Makran. These two of them. And you can see that the plate, subducting plate here in blue, and an old bit of the plate, and then in between there is an interruption in subduction. So the subduction was definitely interrupted for a while in this time. As you can see this more clearly here, that slab is down here, up here, but in between it's absent. So that gap in subduction is an important tectonic clue for us. And as you can see in the central Makran, it's a more persistent slab going down, and of course in the easternmost Makran, it becomes a little bit less prominent than the rest of it. Okay, so all of this I've already said. And now here is another dip section, this time in the Pakistan and Afghanistan ranges. And as you can see here also, you can see the slabs, the older slab and this current slab, but with the older parts up here. Again, two bits of slabs under Suleiman range that are old slabs that are now buried, completely buried. And then here in the Hindu Kush, with Western Hindu Kush, you have a slab, and then Eastern Hindu Kush, you also have old slabs. So these are all evidence of location of these tomographic depths is not along the coast, but further through north through Iran, Balochistan, and Afghanistan, covering Kirthar, Suleiman, and western and eastern Hindu Kush. So you can see these cold bits of the slab. This indicates that the history of the region has been much more complex than we have known before. The textbooks have to be rewritten because of this new evidence. Okay, I think since my time is coming to an end very soon, I better hurry up a little bit. So here is another depth slab. Again, I wanted to show you that that the evidence is consistent. Here is the transition zone. This is the upper mantle. This is 110, 240, and 500 kilometer. As you go deeper, it becomes less and less prominent. In fact, cold parts of the slabs essentially disappear at 500 kilometers, but they are still prominent in 240 kilometers. That is the upper mantle, and also in the lower part of the lithosphere, they are still prominent. This one right here. Okay. So I won't. I've already said all of that. Now here is a nice sketch that Dia has made based on all the information that he's gathered from the tomographic images, and you have seen some of these lines already. Here is the Makran looking southwards. Here we are sitting. We are looking at it from the northeast, southward, southwest view, and the Zagros mountains are up here, and the Kirthar Suleiman range are up here, and here is the Chaman Fault, which is the boundary between the Indian plate and the Eurasian plate. And as you can see, there the slab not only is dipping northwards, but it's also tilting north westwards, and even steeper further in Iran. It dips even further steeper. So there is a tear in this slab right here, and so it's a complicated history that is been unraveled for the first time. This is an attempt to understand 3D structure of the Makran subducting slab. Makran coast and Zagros are at the top, and as you can see, the slab is in several bits. Okay, there is also the remnant of an older Indian slab, but with attached to the so this is probably the old Indian slab, which is now attached to the younger Makran slab. Here is the same picture again, a little more in color. As you can see that here is the Makran and Kirthar Suleiman range, and Zagros is right here. The range is right here, and this is another view from the same direction, and also the input sediment input, okay. So and of course this is all based on mapping the slab boundaries with the help of tomography at their depth and their widths, as well as from all those images. And you can see that there are several bits of these things that have been mapped. The tomographic data allows us to trace the extent of the current slab and the older slab underneath Iran, Pakistan, and Afghanistan. And of course, here is a tomographic image of the semi of the hemisphere at different. This is 200 kilometers, 400 kilometers, and 600 kilometers. The reason you can get good tomographic data is because of the earthquakes. The earthquakes generate a lot of good tomographic images. They are strong. They are stronger than any explosions we can use artificially in the ocean, for example, to get images, or on land to get 3D seismic. So we are limited to less powerful, producing less powerful waves, and therefore we have to depend on the earthquakes to do the job. So many of these tomographic images have been created by mapping by the help of earthquakes. And so this is just to show you that the data comes from a global set of data. Worldwide tomographic data now allows geophysicists to image and understand the depth structure of the mantle and overlying crust. With below 200 kilometers, the lithosphere mantle is quite hot. But above that, of course, the subduction plate. And here is a model reconstruction of the subducting flap in the Eocene, Oligocene, and Neogene, as they may have looked. This is just a model. So, you know, how good it is, anybody knows, because the parameters is mostly based on taking the old slab and then moving them back stripping them into their earlier positions, assuming a constant speed, which may not be the right thing to do. So anyway, these are good attempts to understand what these things might be doing in the past. Okay. Now, at the end of this study, Dia has produced a very nice synthesis map, an updated synthesis map of the Makran region and north, further north, this in the study area, and of course, of both Pakistan and Iran. And he has he's put all the offshore and onshore data together, and has made a new map, which is much more detailed with a lot more information. And this, of course, will be published and will be available soon. And of course, now we come to the summary of conclusions. Prior to Eocene, the eastern and western Makran shows stark differences. West Makran was more akin to Arabian neotethys with blue schist exhumation, and East Makran was akin to Indian neotethys, continental and oceanic arc associated with the subduction zone. The Makran Accretionary Prism has evolved as a single geodynamical entity since the Eocene. After the Eocene, it became one unit with near field processes dominating. What are the near field processes? These are the local slab dynamics that are more dominant for Makran from Eocene onwards. Oligocene and Middle Miocene is marked by the growth of accretionary wedge with the clastic source from the surrounding higher relief. This is also a period of transition from dominantly slab dynamics to an advancing trench at the subduction zone, as well as far field influences due to the collision of Zagros in the west. Late Miocene is marked by deformation of the whole Makran accretionary prism and deposition of a major olistostrom or slump deposit, mass transport deposit, as I mentioned earlier, in western Makran as a result of the slab tearing in the west. Plioplasticine saw further isolation of the wedge, greater influence of both far and near field influences with ongoing Zagros and Kirthar collisions, as well as extensive reworking of the wedge. So this is the total history of the Makran. And while Western Makran shows large wavelength fold and fault structures, Eastern Makran deformation is mainly tilted strata towards the coast. The Central Makran shows imbricated thrust with short fold and thrust spacings. Okay, so these are the main conclusion. And now what remains to be studied? Of course, there's a lot remain to be studied. By no means we know everything here. In fact, we've just skimmed the top. Detailed analysis of Makran accretionary prism sedimentary evolution can easily be carried out with existing seismic data. Some of it after reprocessing, especially for the deeper sections, which we haven't done yet. This work was limited to pseudo 3D study of the tomographic data based on 2D data, but by doing a normal 3D study of this data, pre-deformation slab structures can be much better documented and reconstructed. The Makran subduction zone and its accretionary prism is a unique laboratory where subduction dynamics and far field influence can be demonstrated. Lessons learned here could be used for other living and fossil subduction zones around the world. So Makran is a very good example of subduction zone. And I think in future you will see much more interest, international, both international and also from Pakistan in this area. And also I think oil industry is going to become interested in this area again. In fact, they already are interested in this area. We know that. Thank you very much.